Welcome to our course, Minitab Statistics for Second Language Research. This is Lesson 6. In this lesson, we're going to study about effect size and power, and we're going to perform a two-sample paired t-test. This lecture is based on our textbook, A Guide to Doing Statistics in Second Language Research using SPSS and R, translated into Minitab. And this is all in Chapter 8 in our book. Let's define the difference between an independent and a paired t-test. We learned how to do an independent t-test in Lesson 5. In an independent sample t-test, a parametric test that can tell us whether scores of two different groups are statistically different from one another. So basically we are comparing two groups, and we are trying to compare the means of those two groups. When we do a paired samples t-test, this is a parametric test that can tell us whether the scores of two groups where the same people were tested twice are statistically significant from each other. So basically, we have an experiment, and we gather data from a group, and we have two different measures, and we compare those two measures. That's where we would do a paired samples t-test. Let me give you some experiments, and you will decide whether we should apply an independent or a paired t-test. Case 1. Reading attitudes. ESL students randomly received either a scripted or a non-scripted version of a reading program. 20 students from the scripted program were interviewed about their attitudes toward the reading before the semester started, and then near the end of the semester. We want to know whether the students' attitudes changed during the course of the year. So here, in this case, do we apply an independent or a paired t-test? Stop the recording and give an answer. This should be a paired test because we have one group and we have two measures. So this would be a paired test. Here's another case, case 2, reading ability. The same group as before, but now we want to know whether students using the scripted version of the reading program performed better on a reading test at the end of the year than the ESL learners who used the non-scripted version. This would be an independent test because I am comparing two groups. Take another case, case 3, vocabulary learning. Students in an English language institute were randomly assigned to watch an episode of Friends or Seinfeld each day for 8 weeks. A recorded interview with an unknown but same sex and same age native English speaker was recorded for every participant before and after the term. We want to know whether students use more slang at the end of the semester. This would be a paired test. We have one student and we have two measures, and we want to see if there's a difference between those two measures. Here's a case 4. Same group as in case 3. Now we want to know whether there were any differences between the people that watched Friends and the ones that watched Seinfeld groups in the number of slang terms that the students used in the final interview. That would be an independent test because here we have two groups, the group that watched Friends and the group that watched Seinfeld, and then we want to compare those two groups. In the previous lesson, we learned how to calculate a t-value, and you have the formula there. I will not go over the formula. Remember that the program is going to calculate that automatically for you. However, we want to add two more measures so that your reporting will be more exact. The first one is what we call COHEN'S D, and this is usually referred to as the effect size, and you should report an effect size. What is this? COHEN'S D is an effect size that measures the difference between two independent sample means. This is a group difference index of effect size. COHEN'S D can start from 0 and range as high as it needs to, although a D with a value of 1 means that the difference between the groups is as large as one standard deviation, and this would be considered a large difference. Okay, so we're going to learn how to calculate Cohen's d, and this is going to tell us whether there's a large difference or not. And this is the formula for Cohen's d. Again, we don't need to worry about this because the program is going to calculate this for us. Then we're going to define power, and power is basically the probability of detecting a statistical result when there are in fact differences between groups and relationships between variables. In other words, when the null hypothesis is false. If the null hypothesis is not rejected, then we don't measure power. It is suggested that a power of 0.80, 80%, is a good level to try for. Okay, so if we get a power higher or equal to 80, then we will conclude that we have a very strong statistical result. To do this, we're not going to use Minitab. Minitab, remember, is designed for business, so they usually do this before the test, but we want to do it after the test. So we're going to use a different program, and we will call that GPower 3.1, and I will show you how it works and how to download it. Okay, so now we're ready to go to Minitab and GPower 3.1. Let's go. Okay, so here we are in Minitab, and we're going to be using the data in Larson Hall Forgotten. Larson Hall Forgotten. In this data, she has three groups of students. Group 1, as you can see there, Group 2, and Group 3. Group 1 is a group of Japanese learners that have never lived in an English-speaking country. Group 2 is a group that has lived in an English-speaking country when they were adults, and Group 3 is a group that has lived in an English-speaking country when they were children. So we have what we might call the non-livers, the early livers, and the late livers. Okay. Now, in order to perform a t-test, we want to compare here. We're going to compare the early students with the late students, the ones that lived in an English-speaking country early when they were young, and then the ones that lived there when they were adults. Now, to do that, then we have to separate the groups. So to do that, we're going to go to Data, and we're going to unstack the columns. So we go Data, Unstack Columns, and what we're going to do then is we're going to take the sentence accent. Okay, this is what we're going to be measuring. We're going to see how their accent, if there's a difference in accent among these three groups. And we're going to use the subscripts in status, okay? And we want them after the column in use. So we add that there, and we get the three groups. Now remember that I recommend that we label the columns so that they're easy to read, okay? So let's label number 1. Let's call it sentence accent. So we're going to call it sentence accent, and this is going to be the non-group. Okay, the group in C5, this is going to be the sentence accent, and this is going to be the late group. And 3, this is going to be the sentence accent, and this is going to be the early group. Okay, so now we have the three groups there labeled and separated. So now then we are ready to perform a t-test, and this is what we call an independent t-test. Now remember that before we run an independent t-test, we need to check for normality and we need to check for equal variances. Okay, so we're going to do that before we start. So to do that, we go to Stat, Basic Statistics, Normality, and we're going to check, we're going to compare the late and the early, so we're going to check only those two. So let's check then the late first. And remember, we do the Shapiro-Wilk test. So when we do the Shapiro-Wilk test, we got there that it was higher than 0.1. Notice that the points are not really on the line too much. However, we got higher than 0.05. That's what we want. So higher than 0.05 means that the data are normally distributed. So in this case, yes, the late group meets the normality condition. Let's check the late group and see if the late group also meets the normality condition. So we go normality test, and now we're going to test the early group, always Shapiro-Wilk, and we run it. Here we have the line, the points, and notice again we've got a score, a p-value higher than 0.1, which is higher than 0.05. Therefore, we conclude that the late group and the early group both satisfy the normality requirement. The second condition is that they have to meet equal variances. So let's check that. So we're going to go to Stat, Basic Statistics, and we're going to go down to two variances. We're going to compare the two variances. And in this case, we have each sample in its own column, and we're going to compare the late with the early group. We click OK, and notice that we are interested here in the Levine test. So notice that here it says that the variances are equal, so that would give me a ratio of 1. They're not equal, and we got a high p-value. We got 0.85. P high, the null can fly, so that means that the variances are equal. So notice that we have passed the two requirements for an independent t-test. We checked for normality. Each group had normal distribution, and then we checked for equal variances, and we can see then that both groups do have equal variances. So we're ready then to run a test. Remember that you can also view that when you do a graph, and you're going to go here, graph box plot. Okay, so this is also going to give you sort of an inkling of what you can expect. So we're going to compare late and early. Okay, we compare late and early, and we can see here, this is what we're going to be comparing. So here basically, are the means different? Notice that they are not quite the same. So one mean is going to be here and the other one is going to be here. The variances are more or less the same. So the question is whether this difference is going to be significant or not. Again, to make double sure that our result is going to be on the right track, we can run the basic statistics. So let's go to basic statistics, and we're going to compare the late with the early group, and we're going to go here statistics, and what we want is basically the mean. We want the standard deviation. We don't want the minimum. We don't want the maximum. We want the non-missing ends, so we want to know how many samples we have. We want the median. So basically we want the mean, the standard deviation, the n, the number of samples, and the median. That's pretty much all we want. So let's run that. Okay, we're ready. We run that, and we can see that the late group had a mean of 3.1 and the early group had a mean of 4.5. So that looks like there's a big difference there, but again, we need to see whether this is going to be a significant difference statistically. Okay, so we're ready to run then our t-test. So here we're going to go to stats, basic statistics, and we're going to go to a two-sample t-test. So statistics, stats, basic statistics, two-sample t-test, and we have them now in their own column. So sample 1 is going to be my late group, sample 2 is going to be my early group. Okay, and sample 1, the late group, sample 2, the early group, and we click OK. And here we have again the little summary with the different means and the standard deviations. Notice that here we get the confidence interval for the difference. Notice that here the interval does not go through 0. Okay, if the interval does not go through 0, remember, yes 0, yes h0. Now on the other hand, if we have no 0, so no 0, that means no h0. So that means that there is going to be a significant difference. We can double check that with the p-value. Notice that here the p-value is less than 0.05, so the p is low, h must go. So in this case, notice that we reject the null hypothesis. So here then basically we say that the means are not different. The means are not different. Okay, so in other words, there is a difference between the early and the late group. There's a difference, a significant difference between the early and the late group. Now, we already knew how to do all this. So the question now is going to be, is this difference significant? We know that it is, but the question is, what is the effect size that we have here, and what is the power of our calculation? So that's what we're going to do now when we open GPower 3.1. So we're going to open GPower 3.1. It's here. Okay, so that's my GPower 3.1. Okay, let me open again here I will need to have my basic descriptive statistics here. Okay, so I will keep them here, and I am going to put this here. Now here then, this is GPower 3.1.9.4. What we're trying to do here, the statistical test is going to be the difference between two independent means, so two groups. And what we're doing here, we're not doing a priori, we're doing a post hoc, it's called here. So this is, we're going to compute achieved power given alpha, sample size, and effect size. Now what we want to do then is calculate the effect size, but we don't know that, so we're going to calculate that. We need to enter our sample size. Okay, so here group 1, let's make that the late group, is going to be then 15, and then the early group is going to be 14. Okay, we have to enter everything in the right order. Okay, so group 1 is going to be the late group, and group 2 is going to be the early group. Okay, now we need to enter the data, so we're going to go here, determine, and notice that here I need to enter also the standard deviation. So the mean group 1, we said group 1 is going to be the late. The mean was 3.103, and the mean for group 2 was 4.591. Okay, the standard deviation for group 1 was 0.934, and the standard deviation for group 2 was 1.114. Okay, so here we enter then the mean for each group, and we enter the standard deviation for each group, and we calculate. Now when we calculate, this is going to give us an effect size. So notice that here we got an effect size of 1.44. Remember that if we get anything higher than 1, then we have a good effect size. So this means that, you know, there's a big difference, a significant difference between the two. So we got our D size. Okay, we need to report. This is what we call the effect size. So Cohen's D is the effect size. So we need to report that. Here we got a 1.44. We're going to transfer this to the main window so that we can calculate the power. Okay, so we send that to the main window. So notice that now the effect size appears here, where it started with 0.05, and now we click here on determine, and we're going to calculate, and we get our power. So notice that our power here is 0.98. 0.98. That means that we have 98% chance that there will be a significant difference between the two. So that means if we repeat the experiment, there's a 98% that we are going to find a significant difference. So this power is very high, and that was also reflected by the effect size that we saw here. We got a 1.4. Remember, anything higher than 1 means that we're going to have a considerable effect size and therefore a high power. So here then we learned two new concepts. We learned how to calculate effect size, and to do this we're going to be using then GPower 3.1, and then once we calculate the D, Cohen's D, we enter that into the formula here on the left, and then that's going to give us the power for our test. So notice that in this case then we have a 98% chance that if we repeat the experiment we're going to find a significant difference between the two samples. Remember that we can always run the assistant to see whether our results match what we did before. So let's run the assistant. We're going to go to Assistant, Hypothesis Tests, and we're going to get a list of all the tests here. So we look for the two-sample t-test, and what we want here then, sample 1, we want to enter then the late, and sample 1 we want to enter the early. It doesn't matter, the order doesn't matter. So early, late, because we're comparing the two here. And we click OK. Notice that here we're going to get our little cards, and all the information that we tested before is going to be here. It says the mean of the early is significantly different from the mean of the late. Okay, that's what we observed before. So there is a significant difference when we compare the means of the two groups. Here we have a little summary, and here we also have the confidence interval. So this would be interesting to repeat and to report, basically because if someone wants to replicate your study, if their values fall within those values, then notice that your results would be confirmed. Here we have the difference between the samples. We saw that the difference between the samples was 1.488. And here then we had the little chart. We see that the chart does not go through 0. So no 0, no H0. Okay, so in this case we reject the null hypothesis, and then we concluded that there was a significant difference between the two. Here you have a little chart between the two, so you can see that they don't even overlap. So if they don't overlap, notice that they're not going to be comparable at all. Here then we have this little chart we can ignore for the moment, but here now we have a little information about power. Okay, so here this gives us power, but notice that it doesn't give us Cohen's D, and Cohen's D needs to be reported. Now here it basically says that the observed difference was 1.4888. Okay, now notice that here we have the little chart for the power, and we got 1.488. So that means that we are here in the green area. So that means that we have a very strong difference. And we said before that we got, what was it, 98%? So our 88%, we are here in the green area. So that means that we have a very strong result, a very strong difference between the two means. Okay, so now we are ready to learn about the paired t-test. Let's review a little bit about independent samples t-test. Remember, it's a parametric test that can tell us whether the scores of two different groups are statistically different from one another. That's what we were doing before. Now we're going to move on to paired samples t-test, and this is a parametric test that can tell us whether the scores of two groups where the same people were tested twice are statistically significant from each other. So the main difference is then that we have in the independent samples t-test, we have the scores for two different groups, while here we have different scores for one group. So we have the same subject with different scores, and we're trying to compare those scores. That's where we're going to apply the paired samples t-test. The formula for the paired t-test is a little bit simpler than the formula we had for the independent t-test. Here you can see t is going to be then the t value, where d is going to be the difference between the samples, sd is going to be the standard deviation of the difference, n is going to be the number of samples. So we take the difference between the samples, then we divide that by the standard deviation of the difference, and we divide that by then the number of samples, and that's going to give us a t value. Remember that whenever you apply t-tests, you have to keep in mind what we call the degrees of freedom, and in this case this is going to be n minus 1, the number of samples minus 1. We're also going to learn about bootstrapping, and this is a procedure where samples are randomly resampled from the original sample of data to form new samples. We will see how to do that in Minitab, and we will see what the effect of this is. To learn about paired t-tests, we're going to be using the data by Kim 2013. Here she's trying to teach English learners to recognize sarcasm in English, and she's going to give them 3 tests. One before the lessons, 1 week after the 8 lessons, she's going to do this for 8 weeks, and then another 8 weeks after the lessons. It's going to be the same test 3 times, and she's going to have then the 3 subjects with 3 tests. So in this case we're going to be comparing 2 tests at a time, so this is the case where we would need to use a paired t-test. A problem that we're going to see here is that she only had 9 subjects, so we're going to have to learn how to get more robust data. So we're ready now to perform a paired t-test. Let's go. Okay, so here we are in Minitab. We have opened Kim 2013. As you can see, Kim had 9 participants, and each participant got tested 3 times. So we have a pre-test, a post-test, and a delayed test. In this exercise, we are only going to compare the pre-test and the post-test, and I will leave up to you to compare the post-test with the delayed post-test. So let's compare the pre-test and the post-test. Remember that before we run any kind of t-test, we need to check first for normality and equal variances. So let's check for normality for the pre-test. So we're going to go to Stat, Basic Statistics, Normality Test, and in this case we're going to check for the pre-test, and remember we always do the Shapiro-Wilk. So we run that, and we see that we get a p-value higher than 0.05. You can see that the points really stick around the line. So here we do have a normally distributed set of data. Let's do the same for the post-test. So for the post-test, we're going to go again to Stat, Basic Statistics, and Normality Test. And now we're going to do it for the post-test. So we run for the post-test, Ryan Joyner again. And now we see that we also got higher than 0.05, again showing that this is going to be normally distributed. So the 2 variables pass the normality test. Next, we're going to check for equal variances. So what we do is, again, we go to Stat, Basic Statistics, and now we're going to go to 2 variances here. So Stat, Basic Statistics, 2 variances, click, and we have them in its own columns. So we have 2 columns. Sample 1 is going to be the pre-test. Sample 2 is the post-test. Click, and we get our scores here. Remember, we are interested in the scores for the Levine test. So in this case, we have the confidence interval there, and in this case, we get a value of 0.311. P is high, the null can fly. So in this case, it means that actually the 2 variances are similar. We have the same variance, so we have passed both the normality test and also the equal variances test. So now we are ready then to perform the paired t-test. Remember that we're trying to do a paired t-test. So we go to Stat, Basic Statistics, and then we go to paired t. So Basic Statistics, Stat, Basic Statistics, paired t. Okay. Now each sample is in a column. So sample 1 is going to be the pre-test. Sample 2 is going to be the post-test. And we click OK. And as we can see here, we get the little chart with the descriptive statistics comparing 7 and 16, which the mean for the pretest was 7 points, the other one was 16 points. We can see that there is actually a big difference between the two. Then we can see here the estimation for the paired difference. So the difference between these two is minus 9.11. Minus 9.11. So you can see that if you add 911 to 744, you will get 16.56. So this is the 911 that you get here, with a standard deviation of 685. Now here we have a confidence interval of minus 14.37 and minus 3.85. Notice that the confidence interval does not go through 0. So no 0, no H0. So that means then that the two means are not going to be similar. They're going to be different. When we run the test, we see that we get a t-value of minus 3.99 and a p-value of 0.004. 0.004 is less than 0.05. P is low, the null must go. So we see that then in both of these tests we are rejecting the null hypothesis, and the null hypothesis basically saying that the two means are equal. So we are showing here that the two means are not equal. Okay. Now notice that in this case then we ran a paired t-test. Now as always we are going to run the assistant, and if we run the assistant we go to hypothesis test, and in this case we have a paired t-test. We're going to run the assistant paired t-test. We have two measurements. We have a pre-test and a post-test, and we are comparing here this part here. Is the mean of the pre-test different from the mean of the post-test? So that's the setup that we want. It's always set up for 95% confidence interval, so we're fine, and we click OK. And now we're going to get the report from the assistant, and as you can see, it says the mean of the pretest is significantly different from the mean of the post-tests. We already figured that out before. We got a p of 0.004. P is low, the null must go. So in that case, the null was that the two means are different. Here we have the confidence interval for the data. It goes from minus 14 to minus 3. Minus 14 to minus 3. Remember that, because we are going to bootstrap the data. And here then we have the distribution of the difference. Notice that the distribution of the difference does not go through 0. No 0, no H0. So we reject the null hypothesis. Okay, so notice that the p-value and the distribution of the difference here that does not go through 0 both tell us that we have to reject the null hypothesis. Let's see what else the assistant tells us. So here we have the diagnostic report. We can see that we don't have any outliers, so we're fine. Here we have an observed difference of minus 9.111. So we are in the green area, so that means that we have a very strong difference between the two. Okay, so that's good. We have a strong difference between the two. And here it says there are no unusual paired differences. Unusual data can have a strong influence on the results, no problem. Because the sample size is less than 20, normality can be an issue. Okay, so we need to make sure that our data are normally distributed. We already checked that, so we have no problem with that. However, notice that when our data are few, and in this case it says less than 20, then we do have to be careful. So in this case, because we have very few pieces of data, this is where we might need to do a bootstrap. To do bootstrapping, we go to Calculator, Resampling, so Calculator, Resampling, and then bootstrapping for 2 sample means. So Calculator, Resampling, bootstrapping for 2 sample means. Click OK, and we have them here in its own column. Okay, sample 1 is the pretest, sample 2 is the post-test, and we want 1000 resamples. Okay, click Options. Now in this case, you have to make sure that you have the two-sided, because we're comparing, they're the same, not the same. And let's store the differences in the column. Okay, so let's click Store here and click OK, and click OK again. So as you can see now here, notice that now we have 1000 cases. Okay, so what the program did, if you go down all the way, see it goes all the way to 1000. What the program did is that it went to your data, and from your own data it took 1000 samples. Okay, so now actually we have an experiment with 1000 samples. Okay, now as you can see here, now this changed a little bit compared to what we had before. Okay, so before, let me see if I find here the 95% confidence interval that we had before. Before we went from -14 to -3. So here we see that we have a span of about 11 units. Okay, 11 units. Now we went from -12 to 5, so now we have a span of only about 7 units. So we can see that our confidence interval got smaller, and that's because we have more samples. Okay, however, we do not go through 0 yet. Okay, so notice that here we don't have a 0, so no 0, no H0. So I am still rejecting the null hypothesis. Okay, so when you report your data, you can report both confidence intervals. So you can say that the normal confidence interval is going to be -1437 to -3.85, no 0, no H0. And if you bootstrap the data, then you still have no 0, and you go from -1244 to -522. Okay, so this is what bootstrapping does to you. Okay, it kind of you can be more certain about your results, but of course this depends on whether the original 9 samples that you had there are representative of the whole population. Okay, so now we're going to go to GPower 3.1. So let's open GPower 3.1. Okay, here we have it. And in this case then, make sure that you have test family. We are running a t-test, and in this case we are running here, this is called difference between 2 dependent means, matched pairs. So make sure that you include here matched pairs. And then here we're not doing a priori, we're doing a posteriori, so we should do post hoc. Okay, compute achieved power given alpha, sample size, and effect size. We have that. Here we're doing a two-tailed test. So make sure we have a two-tailed test, and we have 0.05. That's going to be then the margin of error that we want. Now we're going to enter our data. So here, let's take group 1 to be the pretest group. So we had a mean of 7.44. For the group 2, we had 16.556. The standard deviation for group 1 was 5.25, and the standard deviation for group 2 was 2.9 0.63. Okay, so we enter that. Now notice that here is asking us for a correlation between the two groups. So we actually need to run a correlation, so we can enter this here. Otherwise, it's going to give us the default 0.5. So we need to run a correlation. Make sure we run a correlation. So let's go back to our Minitab, and we need to run a correlation then. So basic statistics, and here then we're going to do a correlation. And we're going to do the correlation between the pre-test and the post-test. We run the correlation, and here we're going to get an R value. Now in this case we got an R value of minus 0.340, minus 0.340. So we need to enter that here. Okay, so we're going to go correlation minus 0.340. Now once we enter that correlation, and make sure you enter that correlation, you click here calculate. Now we calculate an effect size of 1.33. This is higher than 1, and 1 is basically a very high level. So what we do now is we transfer this from this window to that window. Now the way to do that is we calculate and transfer to the main window, and notice that that 1.33 has automatically been entered here. Now here, make sure that we have the correct data. So you need to have two tails. You need to have the effect size that was transferred from that window. We still work with a 95% confidence interval, so this is fine. But notice here that the total sample size in our case is 9. So we make sure that we include here the total sample size. If you remember, when we did the GPower for the independent t-test, we had two boxes here for sample sizes, and that's because we had two different samples. Here we only have one group, right? The other case we had two groups, so here we only have one, and we have 9 subjects. So we click now calculate. So we are ready here. We have all the information. So notice you need to enter the mean, the standard deviation. That automatically will transfer to this window. Here you make sure you have two tails. Make sure that you have the correct sample size. Make sure that here test family you have a t-test. Here you have means, difference between two dependent means, so you have matched pairs, and here you have post hoc. Now you click calculate, and we get a score of 93.62%. 93.62%, which is again very high, and we knew that because we got a value here higher than 1.3. If you look at this graph here, you see that there's an alpha and there's a beta. We will talk about alpha and beta. This is what we call the type 1 and the type 2 error. We will be talking about these guys next week. Alright, so this then takes care of COHEN'S D and also the power. So in this case, notice that we got a power of 93.62%. So that means that with the model that we have, we can predict 93.62% of the variation that we had between the two means, between the pre-test and the post-test. Let's go back to our statistics here, the last one, and let's check what is said for power. Notice that it says minus, the observed difference was minus 911, okay, and then the difference 9 was here. So notice that 911 is a very high point of difference, okay. So here then, that's why that was in the green area, but our power then was very, very high. Okay, we are now ready to summarize what we have learned in this lesson. The main goal for this lesson was to teach you how to perform a paired t-test. And here on the left side of the screen you have the formula. So to calculate the t value for the t-test, what we do is we take the difference between the samples, and then we divide that by the quotient of the standard deviation of the difference divided by the square root of the number of samples. We must keep in mind also that the degrees of freedom in this case is n minus 1. We also learned how to read the results of a t-test in general, and that includes the independent t-test and also the paired t-test. One way then is to compare the t-value that we get for our test and the critical t-value. And then this is going to define two areas. One area is going to be that do not reject the null hypothesis, and the other one is reject the null hypothesis. So depending on where the t-value is going to fall, we're going to reject or not reject the null hypothesis. The second way to do this is to compare the p-value with alpha, where alpha typically is going to be 0.05. So if p is higher than alpha, we do not reject the null hypothesis. And if p is lower than alpha, then we reject the null hypothesis. Here, remember our song, which says p is high, h null can fly. So in that case, we do not reject. P is low, h null must go. We reject h0. The third way to do this is to read the confidence interval for the mean difference. When we get the confidence interval for the mean difference, we're going to get two values. And if 0 is included in those values, or between those two values, we do not reject h0. So remember, yes 0, that means yes h0. So in that case, we do not reject the null hypothesis. And remember, no 0, no h0. So in that case, we reject the null hypothesis. So all we need to do is basically see whether 0 would be included in that interval. And if it is included, then we do not reject the null hypothesis. If it's not included, then we reject the null hypothesis. Also, we learned how to run GPower 3.1 to determine two values. The first value is what we call COHEN'S d, and this measures the effect size. And remember that this is measured in standard deviations, and if we get any value higher than 1, then that would be considered a large effect size. So if you get 1 or higher than 1, that's a large effect size. Now with that effect size, we also calculated the power, and in this case the power is the probability of detecting a statistical result when there are differences. And in this case, remember that if you get power higher than 0.80 or 80%, that would be considered a good solid difference. Alright, so now we are ready then to discuss your projects for next week. The first project we already talked about, and this is Kim 2013, and the name of the paper, in this case is an unpublished dissertation at Pennsylvania State University, is called Developing Conceptual Understanding of Sarcasm in a Second Language Through Concept-Based Instruction. We already talked a little bit about the data, and we already saw whether there is a difference between the pre-test and the post-test. So here then, your mission is going to be to answer this. Is there a statistically significant difference between the post-test and the delayed test? Include the value for the t-test, the corresponding p-value, and the confidence interval for the mean difference. How do you interpret those results? Remember that Kim had only 9 pieces of data. So then what you're going to do here, you're going to bootstrap the data, and then you're going to report the new confidence interval. And then finally you're going to write up the results following the model that I gave you in the video. That's project number 1. Project number 2, you're going to be working with old data again. This is from Larson Hall and Connell, 2005. Remember that they were testing kids in Japan, and here they had 3 groups. One was a group that had never visited an English-speaking country. The group number 2 is the group that they went to the English-speaking countries, but they were late visitors. And group number 3, they were early visitors. So there are 3 groups. And here, there's some new data that I added to the file. This is about the pronunciation of L and R in English when they start a word, at the beginning of a word. So then here, the question you're going to try to answer is this. Did participants perform the same way with their accent on words beginning with L and R? You're going to report t-value, p-value, and the confidence interval. Explain your conclusion. Number 2, you're going to report effect size and power. Explain your results. Number 3, report your results for the individual groups. As we saw before, you have 3 groups, so you need to do the calculations for each individual group. And 4, you're going to write up your findings. And this brings us then to the end of lesson 6. I hope you found this lesson useful. In this lesson, we learned about effect size and power, and also we learned about the paired t-test, and we learned how to perform a paired t-test. So that's all for this week. Hope you have a good week. See you again next week, and stay well until then. Bye-bye now.